How do marine heat waves impact the movement of carbon dioxide between the atmosphere and the ocean? What are the impacts of the flux? Hello, friends. Welcome to Science Talk. This is Jim here. Okay. This was a paper that was published on the 2nd of January, 2024. The impact of marine heat waves on the air-sea CO2 flux along the U.S. East Coast. It was published in Geophysical Research Letters. The lead author is Kelsey Edwing, and with several co-authors. Okay, this is a really interesting paper. Kind of right to the point, which I like. And I will leave the URL in the comments section. And in addition to in the description of the video as well, since some folks prefer seeing it there. Okay, so let's look at the abstract. Marine heat waves, abbreviated as MHW, are extremely warm ocean temperature events that significantly affect marine environments. But their effects on the coastal carbonate system are still uncertain. In this study, we systematically quantify marine heat wave impacts on air-to-sea carbon dioxide flux anomalies, and they abbreviate that as FCO2 prime. A little apostrophe thing there. In the Mid-Atlantic Bight, MAB, and South Atlantic Bight, SAB, from 1992 to 2020. During the longest marine heat wave in both regions, oceanic CO2 uptake capabilities substantially decreased. Right? During the longest marine heat wave in both regions, oceanic carbon dioxide uptake, the ability for the oceans to absorb CO2, substantially decreased, primarily due to significant increases in the seawater partial pressure of CO2, abbreviated as small case p CO2, SEA, all as subscripts. Okay. So when the seawater partial pressure of CO2 goes up, the ability to absorb CO2 from the atmosphere goes down, inversely related. And of course, we tie in the fact that warmer water temperatures decreases gas solubility. That also plays a role. For all cases, marine heat waves played a more significant role in driving the partial pressure of CO2 in the ocean changes in the Mid-Atlantic Bight than the South Atlantic Bight, where non-thermal drivers dominated the partial pressure of CO2 in the ocean variability. In the Mid-Atlantic Bight, weakened wind speeds related to wintertime atmospheric perturbations increase ocean temperatures and the partial pressure of CO2, further reducing CO2 uptake during winter marine heat waves. This work is the first to connect extreme temperatures to coastal air-sea fluxes, CO2 fluxes. The reduction in CO2 absorption noted during marine heat waves in this study has important implications for coastal regions to act as continued sinks for excess CO2 emissions in the atmosphere. Okay. What are the key points? Marine heat waves primarily generated positive sea surface partial pressure of carbon dioxide anomalies in the Mid-Atlantic Bight and South Atlantic Bight, but had a larger impact on the air-sea CO2 flux anomalies in the Mid-Atlantic Bight. Reduced wind speeds amplified marine heat wave contributions during the months where you expect CO2 to be a sink, and counteracted them during the CO2 source months. In the mid-Atlantic bight, wintertime atmospheric perturbations related to zonal shifts in the jet stream produce slower wind speeds, which aid in generating air-sea heat flux type marine heat events that ultimately reduce oceanic CO2 uptake. This, to me, is a really important finding. So let's highlight this. Okay. In the mid-Atlantic bight, now we're talking New York, New Jersey, that area, Long Island, right? Wintertime atmospheric perturbations related to zonal shifts in the jet stream, and they have a diagram that we'll look at later to model this. So perturbations related to zonal shifts in the jet stream produce slower wind speeds, which aid in generating air-sea heat flux type marine heat events that ultimately reduce oceanic CO2 uptake. Okay, simple language. Wind speed slows down, the heat persists, there's no evaporative cooling, so hence the waters are warmer, they can't take up the CO2. Basically what the ultimately saying there. Okay, let's look at the plain language summary. The transfer of CO2 between the atmosphere and ocean is sensitive to sea surface temperature changes because warmer sea surface temperatures increase the sea surface partial pressure of CO2 and reduce the ocean's ability to absorb CO2 from the atmosphere. And also warmer waters, the gas solubility is less, which is what is meant by increasing the partial pressure. If you increase the partial pressure, you're not going to be able to absorb much more. So the warmer waters has that effect. It increases the partial pressure of CO2, reduces the solubility of further gas absorption. It is therefore conceivable that marine heat waves, which are extremely warm ocean temperature events, could modify how carbon moves between the ocean and the atmosphere. This study provides the first attempt to evaluate the impacts of marine heat waves on the air-sea CO2 flux anomalies along the U.S. East Coast. Basically, the Mid-Atlantic bight, the South Atlantic bight, from the aforementioned 92 to 2020 years. Both regions experience reduced CO2 absorption in response to the longest marine heat wave in each region. These extreme temperatures had a larger impact on CO2 absorption in the Mid-Atlantic bight compared to the South Atlantic bight. Coastal ocean plays an important role in helping to mitigate human-induced climate change by absorbing excess CO2 from the atmosphere. As such, the demonstrated reduced absorption of the ocean associated with marine heat studies in this study, which might also apply to other coastal locations, has vital implications for the efficiency of the ocean in offsetting global warming impacts. Okay, before we proceed, we have ocean heat content. As the stratification increases and intensifies, you're not going to sequester the heat to depth. And then that starts fluxing. It increases the sea surface temperature, reduces the solubility of the gas. It can't absorb CO2 from the atmosphere, and may also, with the warming temperatures, CO2 will outgas from the ocean back to the atmosphere. Okay, so let's take a look at what they are saying here in the introduction. Anthropogenic climate change exhibits extensive effects on the global climate system, notably resulting in rising air and sea surface temperatures and increasing the prevalence of extreme events. Basically, heat energy driving, precipitation bombs and nasty storms. The ocean is currently estimated as a net sink for atmospheric CO2. leading to fundamental shifts in Earth's climate system by absorbing approximately 25% of anthropogenic carbon emissions since the pre-industrial era. Okay, 25% of CO2. When we talk about ocean heat content, we're talking about heat energy. So these are two different measures. Hopefully, we want to clarify that point. However, CO2 uptake could be weakened due to the prevalence of extreme events such as marine heat waves. Marine heat waves are prolonged, anomalously warm seawater events that can persist for days to months and range in size up to 1,000 kilometers or more. They have increased in frequency, intensity, and duration over the past 2 centuries and occur frequently in the eastern continental margins of the United States. However, their influence on the carbonate system parameters like partial pressure seawater of CO2 and therefore the air-sea CO2 flux is insufficiently investigated. Air-sea flux, CO2 flux, quantifies the exchange of CO2 between the atmosphere and the ocean. The difference between seawater partial pressure and atmospheric partial pressure. So note the subscripts here. We have P, the small case P is partial pressure, CO2, the C, same thing, but with air, okay? The difference there, given as delta P, CO2, determines whether the ocean is taking up CO2 from the atmosphere, which is indicated by a negative value, or emitting CO2 to the atmosphere, indicated by a positive delta P value. Okay, so let's highlight this. So we have this clear. Okay, if the delta P CO2 is negative, CO2 is going into the oceans. If the delta P is positive, CO2 is going to the atmosphere. Okay? Spatial and temporal variations in the partial pressure, CO2 in the atmosphere, are small, so delta P CO2 variability is primarily controlled by variation of the partial pressure of CO2 in the ocean. Spatiotemporal partial pressure CO2 in the ocean changes are driven by thermodynamics, mixing, biological activities, air-sea gas exchange. Since marine heat wave events are extremely warm sea surface temperature events, it is conceivable that marine heat waves could impact the partial pressure of CO2 in the ocean and therefore the flux of CO2 via thermodynamics. So they go on to say that the literature is limited on this, okay, and how they want to understand. So they're looking at the focus, the study on the Mid-Atlantic Bight, which is here. That's supposed to be Long Island, so there's Rhode Island and right, whatever. New York, New Jersey, right? South Atlantic Bight, probably down to like Georgia. Yeah. Anyway. So this is the two areas that they're focusing on. They split into the MAB and the SAB location, but it's basically pretty much up the eastern seaboard up to pretty much Cape Cod, in essence. Though regional differences in physical and biological processes exist, both the MAB and SAB have been consistently estimated as net sinks of atmospheric CO2, with the Mid-Atlantic Bight CO2 flux density estimated as negative 0.73 to negative 1.9. This is moles of carbon per square meter per year. Okay? And for the SAB, it's minus 0.48 to minus 0.75 moles of carbon per square meter per year. What's a square year? It is found that the partial pressure of CO2 in the ocean variations along the U.S. East Coast reflect local, short-term modifications by coastal physical and biological processes, such as Ekman pumping, onshore pumping, Ekman downwelling, Ekman upwelling, that kind of stuff. Wind speed and direction. Do we have winds blown across, blowing, say, in a zonal direction or blowing in a meridional direction, i.e., perpendicular to the coast or with the coast? That will impact because wind blows and moves the water, it'll impact what the physics of the water does. Under extreme cases, such as marine heat wave events, the partial pressure of CO2 in the ocean and therefore the flux of CO2 may be more sensitive to significant increases in sea surface temperature and potentially switch coastal CO2 sinks to sources for the atmosphere. May be more sensitive to significant increases in sea surface temperature and create a situation where the oceans, instead of being a sink for CO2, becomes a source of CO2. So it goes back to the atmosphere. So the study looks to examine all of that. Okay, they have a section on the methods and so forth. As I said, I'm leaving the URL to this paper in the comments and in the description. So you can pull that up and read through this if you are interested. I'm kind of going to skip over a lot of it of mathematics. Okay, whatever. Although it's interesting, they use the Taylor expansion. So it's a series analyses. Okay, let's get right to the results and the discussion. So the two most prolonged marine heat wave events in the Mid-Atlantic Bight and South Atlantic Bight. So they looked at, to examine this question, the overall study, they looked at the changes here. The longest event in the Mid-Atlantic Bight lasted over 200 days, 25 November 2011 to 15 June 2012, and was named the 2012 Mid-Atlantic Bight event. Analysis focused on the overlapping period between the marine heat wave event and available SOCAT observation from February 2012 to June 2012, a length of 5 months, which is Figure 1A. We'll look at Figure 1A in a moment. The longest marine heat wave event in the South Atlantic Bight, referred to as the 2017 SAB event, lasted 44 days and was basically 21 March of 2017 to 5 May 2017. To maintain the definition of a marine heat wave month, analysis focused on April 2017, Figure 1B, as the event lasted fewer than 15 days in March and May. And apparently, for some reason, because of like half a month, or less than half a month, they don't consider it to be marine heat wave months. You could have just used Julian days. Julian days. January 1 is Julian day 1. December 31st is Julian day 365 or 366 if it's a leap year. You can just use Julian days. That would probably make more sense. Okay, so I'll pull this up and we'll look at it in a large view in a moment, but let's see what the description is. During the 2012 the Mid-Atlantic Bight event, sea surface temperatures anomalies exhibited a significant increase in the initial 3 months, February through April, followed by a gradual decline in May and June, Figure 2A. Okay. Therefore, we divided the 2012 MAB event into the early period and the later period following those months. During the early period, the partial pressure CO2 in the ocean anomalies experienced no significant difference, but a substantial surge of approximately 46 microatmosphere above the climatology in May and remained notably positive until June. And they give the values plus basically 37 plus or minus 12.7 microatmospheres. That's figure 2C. This increased partial pressure CO2 impedes air-sea CO2 exchange, since the air-sea partial pressure CO2 gradient becomes smaller. And when gradients become smaller, that means they're almost at equilibrium. Exchange rates slow down. Additionally, the wind speed was negative 0.42 plus or minus 0.34 meters per second, lower than climatology throughout the entire event, which also impedes CO2 uptake. If you have a slower wind speed, there's less mixing. It's as simple as that. Consequently, the average CO2 flux anomaly is positive. And what did we say earlier? If delta P is positive, then that means CO2 is moving from the ocean to the atmosphere. Okay, so let's see if we can. Here we go. And let's take a look at the caption first, and we'll go back to here. So monthly values are in blue. Climatology are in black. Anomalies are in red of A and B sea surface temperature, C and D sea surface partial pressure CO2. E and F are wind speeds. Okay. G and H are SSS, the sea surface salinity. And I and J are the flux of CO2. So this is during the 2012 MAB, which are the left panels, and the 2017 SAB, which are the right side panels. Okay. Blue squares in each plot highlight the 2012 and 2017 marine heat wave events in the mid-Atlantic bight on the left and South Atlantic bight on the right. Error bars are one standard deviation associated with the monthly climatology in each panel. Okay, so keep in mind, this left side is the mid-Atlantic bight. This right side is the South Atlantic bight. So they have the sea surface temperature, the partial pressure of CO2 in the water, right? Both sides, the wind speed, sea surface salinity, and the flux. And the flux, a reminder, it's in moles of carbon per square meter per year. And the blue box is what they're kind of calling the marine heat wave itself. Okay. And when you compare the average, okay, right, the ocean should be cooling down. This is what it was. So you can see why they called it, the red dash line. You can see why they call that a heat wave. It is considerably greater than what it should have been. Now keep in mind, this is 2012 for the Mid-Atlantic bight. What was 2023 doing? We saw sea surface temperatures, 6 standard deviations off the charts. Now you're going to say, well, let's look at the sea surface temperature for the South Atlantic bight. Overall, it seems to be warmer than Mid-Atlantic bight. Well, it's further south in latitude, that's why. And there's that narrow time frame for the marine heat wave, and you can still identify a marine heat wave from basically March 17 to May 17, 2 months there. That's why I say I think the use of a Julian day is preferable here. You just have 1 through 365 along the x-axis. All you need to do. In all honesty, that's how I used to present my data. I use Julian day. And we see the partial pressure of CO2. We see it goes a little higher than the observation or the climatological record before dropping off. And here it's closely tracking with the actual observation. Wind speed is definitely lower. And sea surface salinity. So what is sea surface salinity doing? Well, it's a little bit higher, which is interesting because you would expect with let's see where the wind increases in speed, like over here. See, the wind increases in speed, and we really don't see too much of a change in sea surface salinity, though it is notably higher. Usually with an increase in wind speed, you have the mixing, but it also enhances evaporation. So you're removing fresh water, so the salinity, same amount of salt, but there's less water, so the salinity should increase, is the expected result. Now, here, with the slowdown in the wind, there's going to be less mixing, so it'll be less evaporation. I would actually expect to see salinity pretty much close to the average. It's just slightly higher. So the question is this statistically significantly higher or not? And I think they do present some statistical analyses on that later on. Here's it's pretty much tracking the same. But notice the flux increase, especially here. That means CO2 was moving from the oceans to the atmosphere. So we can see that here. And that's what they're indicating. And they go on to describe that for the SAB, the South Atlantic Bight event, provides information of the CO2 changes in its flux during the marine heat events. Both sea surface temp and the partial pressure exhibited positive anomalies before and after. In April, however, both parameters showed a notable increase, much higher than typical. Right? We just looked at those figures. As always, you can always pause the videos and look at them, read these precise values, study, scrutinize the diagrams, what have you. And they go on to this, as we described, they go on to discuss how the wind speed decreased in April and so forth. So they're just now verbally describing what we just looked at in the figures here. In both the 2012 and 2017 marine heat wave events, flux anomaly was anomalously positive. So what the question is the change in the partial pressure to CO2, is it that or the wind speed that explains this? A monthly breakdown of these contributions during the 2012 Mid-Atlantic Bight event, and they refer to supplementary figures here, supporting information S1. If you pull up the URL, click on here. And then you can, let's see if I can, there we go. It's using a PDF. And this is a material that's considered not necessary for the main paper, but it's added there. And you can see it's kind of very bare bones. And contributions to air CO2 flux anomaly during the 2012 and the 2017. So horizontally is the 2012, and 2017 is the bottom set of panels. And the dark blue is CO2 partial pressure. The light blue is wind. That's basically the same. Again, showing marine heat wave. So this is some extra material that they include. As I said, you can pull that up if you are so inclined. So what they're saying was that in 2012, the change in partial pressure CO2 was the primary contributor during 3 of the 5 months, and then so basically February, May, June, while March and April, wind speed dominated. That's all. So understanding whether the thermal, for example, marine heat wave, or non-thermal drivers of the partial pressure CO2 were controlling the partial pressure of CO2 in the ocean anomalies during each marine heat wave event will determine whether the marine heat wave or non-temperature factors were responsible for inducing the positive flux that was noted. During the 2012, non-thermal drivers counteracted the thermal contribution from the marine heat wave during the early period of the event, but not so later on. Thus, processes controlling non-thermal changes in the partial pressure CO2 are potentially important buffers against marine heat wave events because they can counteract either all or part of the marine heat wave's thermal influence on the flux. During the 2012 event in the SAB, the marine heat wave was not primarily responsible for the large magnitude of the flux seen in April. So non-thermal parameters dominated during that event. That's what they are reporting. So they're saying while non-thermal changes in the partial pressure, it may be proved important in both regions, they need to understand the processes of why that parameter is as important as it seems to be. However, without water column total alkalinity and dissolved inorganic carbon data, a definitive answer regarding the mechanisms is beyond the study. Okay. So they go on to report that work by Jones et al. In 2014 on the CO2 gas exchange timescale allows us to broadly hypothesize possible mechanisms. Assuming that open ocean timescales are the same in adjacent coastal regions in the SAB region, the gas exchange timescale is longer than the mixed layer residence time. So in this case, mixing processes are vital controls of the partial pressure of CO2 in the ocean and changes in that. In the Mid-Atlantic Bight region, the opposite occurs. The gas exchange timescale is shorter than the mixed layer residence time. Consequently, mixing is not a dominant control on gas exchange. Instead, our results suggest that the timescale of thermally induced changes to the partial pressure of CO2 in the ocean resulting from marine heat waves in the MAB is shorter than that of air-sea gas exchange. This further highlights the importance of temperature as a dominant control in the air-sea gas exchange in the MAB compared with non-thermal drivers. Non-thermal changes in the MAB during the 2012 marine heat event were likely biologically driven, as the bulk of the event occurred during the time period of the spring bloom. You get mixing followed by stratification, and the phytos do their thing. And what are the phytos going to do? They're going to use CO2 that's in the water. That will do what? That lowers the partial pressure of CO2, allows for CO2 from the atmosphere to move into the water. So that creates, so if you were to calculate the delta P, it would be tending negative, or at least having lower values. So that is a proposed mechanism that they are hypothesizing. To assess whether the significant changes in the PCO2C and the CO2 flux observed during the most prolonged events are representative of all marine heat wave events, we statistically compared the partial pressure and the flux anomalies between marine heat wave months, non-marine heat wave months in the two regions. Over the 28-year study period, 92 to 2020, the ensemble mean flux anomalies during the marine heat wave months in the MAB and SAB were as follows. 0.13 plus or minus 0.63, so big error. 0.26 plus or minus 0.82, another big error. Moles of carbon per square meter per year, respectively. They showed only slight differences compared to non-marine heat wave months. And 0.12 plus or minus 0.81, that's minus 0.12, and minus 0.14 plus or minus 0.96 moles of carbon per square meters per year. While the ensemble mean flux anomaly during marine heat wave month is statistically different from the non-marine heat wave months in both regions, and they give you the p-values 0.03, 0.01, so it sounds like they're using a 95% level. The large standard deviations indicate that a marine heat wave alone is not a sufficient condition for the occurrence of positive flux anomalies. To identify conditions in which marine heat waves will associate with significant positive flux anomalies, we further divided the marine heat wave months into two categories, those above and below the 75th percentile. Okay, 75th percentile is basically one of those numbers of the 5-number summary where you have the median and then you have the Q1 value, the first quartile, which would be the 25th percentile, and then you have the third quartile, which is the 75th percentile. So therefore, the values between the 25th and the 75th percentiles is called the interquartile range. And the median is actually considered to be the second quartile or the 50th percentile. In other words, that's 50% of your data. So they were using a 5-number summary here is what they were doing. And you might be familiar with those things called the cat and whisker plots. right? I'll show you some right down below. So they're talking about the 75th percentile and that the flux of the CO2 value plus 0.54 in the MAB plus 0.84 in the SAB. This helps to distinguish whether marine heat waves or non-temperature factors are responsible for producing large positive flux anomaly values. That is, those that fall above the 75th percentile. Both the 2012 and 2017 events fell above the 70th percentile threshold. In the MAB, temperatures exert a more significant influence on the partial pressure changes than other drivers during all marine heat wave events, and they reference figure 3A. Above the 75th percentile, both thermal and non-thermal drivers are important for producing a large positive flux anomaly, figure 3B. So they go on A, B, C, D, E, F across here. Thermal contributions are usually larger than non-thermal influence, but the means of the two components are not statistically significant, p-value 0.1. Nevertheless, temperatures remains the primary contributor to the anomalies, accounting for approximately 68% of the total changes in the partial pressure. Like the early period of the 2012 MAB event, non-thermal drivers tend to counterbalance the impact of temperature during all months. Now, I'm going to finish reading the verbiage here, then we'll go back and look at figure 3. However, in the marine heat wave months above the 75th percentile in the MAB, non-thermal drivers amplify thermally induced positive changes in the partial pressure anomaly rather than offsetting. That's important. In other words, what they're basically getting at here is if you're trying to identify one single factor, don't. You're going to try, as they just identified for the MAB, the Mid-Atlantic Bight, thermal factors was a main driver, over 50%, 68% of it. So that's a huge contributor. But there are also other events that, in addition, help amplify the effects seen. Remember, when you have various elements interacting, they can either amplify each other or basically mitigate each other, right? So in certain cases, in certain times of the year, non-thermal mitigates the thermal. Other times of the year, it helps enhance, amplify the thermal. Now keep in mind, they're looking at 2012. I bet you if they were going to do this for 2023, it would be a completely different set of findings. Furthermore, the importance of non-thermal processes as drivers of flux anomalies increases relative to the thermal component because, unlike marine heat wave months below the 75th percentile, there is not a statistical difference between the two components during marine heat wave months above the 75th percentile. In general, right, marine heat waves produce a temperature-induced increase in the partial pressure CO2 in the ocean that is somewhat offset by non-temperature factors in the MAB. This is consistent with Mignol and others in 2022, results in a North Pacific subtropical gyra. Now, for the SAB, the initial comparisons of all marine heat waves in this region to those in the MAB indicate that the magnitudes of thermally induced changes in partial pressure in the SAB are similar to those in the MAB, with non-thermal drivers also playing a reduced role compared to marine heat waves. However, statistical analysis reveals that the thermal and non-thermal components are not statistically different, p-value 0.17. meaning non-thermal processes exert a greater influence in the SAB during marine heat wave months as observed in the 2017 event. Like the MAB, non-thermal drivers in months below the 75th percentile offset the impact of high temperatures, resulting in partial pressure anomalies close to zero. However, for months above the 75th percentile, the main contribution to the CO2 partial pressure anomalies comes from non-thermal drivers rather than extremely warm temperatures. This suggests that high partial pressure CO2 values during marine heat wave events in the South Atlantic Bight are not solely caused by temperature itself. So it is inappropriate to conclude that marine heat wave events have significant impacts on CO2 flux in this region. Got to stress that. In this region. Unless the non-thermal drivers also produce a positive partial pressure during marine heat wave events. While marine heat waves appear to play a larger role driving air-sea gas exchange in the mid-Atlantic Bight, prolonged marine heat events like the 2012 MAB and the 2017 South Atlantic Bight events can still produce a noticeable impact on interannual scales. The impact of these two events on the interannual variability of air-sea CO2 flux anomalies is evident in figure S4. The year in which the two most prolonged marine heat waves occurred correspond to some of the highest annual flux anomalies over the 28-year study period. So while non-thermal flux drivers are vital to produce large flux anomalies, especially in the SAB, prolonged marine heat waves are still a necessary condition to produce large changes in air-sea CO2 flux. Let's go back over to here and look at S4. So here's the annual flux anomaly. So negative, positive. So remember, positive means going back to the atmosphere. And we can see, so 2012, here's 2012. And this apparently looks like 2007 or so. So here's some heat wave, and we see a positive flux. That means more CO2 to the atmosphere. 2017 is here. And it looks like they're getting another one here in 2020. So that's what they're saying. So now let's take a look at figure 3. Okay, so pull up the caption here. Mean and one standard deviation, the error bars, right? That's these guys here, of the thermal, which are in light blue, and non-thermal in dark blue. Let's see, so we have here the partial pressure CO2 anomalies in the MAB, that's A through C. So this is for all months above the 75th percentile, months below the 75th percentile. And then they do the same thing for the SAB. P-values for some students' t-tests are in red here. Okay. Determining whether thermal and non-thermal components are statistically different from each other in each panel. Okay, so here's what I'm talking about. So this blue box would represent the interquartile range. Okay, median's probably in here somewhere. And these are your outliers. Now they looked over a 78 months. That's basically 6.5 year period. This is 20 months, 58 months, so on. But they're looking at, for all the months, the p-value was less than 0.001, meaning that there is a difference between these, right? You can see where they're sitting. One's sitting on the negative side, one's sitting on the positive side. This one, there's no significant difference. No significant difference. Right? P-value 0.1. And then below the 75th percentile, very, very different. 7.92 times 10 to the minus 14. I think you can write a 0 there. Anyway. And then for the SAB, South Atlantic Bight, all the months was not different. And for these other two, above and below the 75th percentile, they were. So what this is telling us is that where there is a difference, one of them is causing more of the difference, more of the changes seen in the partial pressure. And since they're focusing on marine heat waves, they're basically saying marine heat waves is the main driver, not the main driver here. They're both contributing, and or one is mitigating slightly. Okay? Main driver here, not significantly different. So marine heat waves is not the main driver of the changes in the partial pressure CO2 in the ocean. Probably both working synergistically. There is a difference, but here it would seem to be that it's more non-thermal, while here it seems to be more thermal. This is basically what this figure is telling us. Okay, now comes what I think introduces an excellent aspect to this. And this diagram basically sums up the study, and it's really important, and we'll look at that shortly. So let's consider wind speeds, the changes during all the marine heat wave months. We also examine wind speed changes, since wind speed significantly impacts the magnitude of air-sea flux. Faster wind generally resulting in higher gas transfer velocities, indicated in K, and larger flux values. Wind speeds were below the average during the most prolonged marine heat wave events in both regions. These slower wind speeds amplified marine heat wave influences on the flux by further decreasing the CO2 sink in wintertime months, counteracting the effects in summertime months, right? Because the oceans are warming up to begin with anyway in the summertime. So what they're saying is a slower wind reduces the fluxing, reduces the absorption in the oceans of CO2, leaving more CO2 in the atmosphere. But when you have the marine heat wave running full bore, at least especially in the MAB region, that increases the partial pressure of CO2 in the ocean, that decreases the flux. Well, it decreases the flux rate because the winds slow down, but you're going to have a positive delta P value, meaning that there is CO2 moving from the oceans to the atmosphere. So now they describe here the figure 4. Reduced wind speeds were typical during many marine heat wave months. Yet, like the partial pressure, further investigation revealed that wind speeds did not significantly deviate from climatology, those long-term averages. However, among the 20 marine heat wave months above the 75th percentile in the MAB, 12 occurred during the wintertime when the MAB typically acts as a CO2 sink. During these events, wind speeds were slower, reduced by minus 0.3 plus minus 50 meters per second compared to average, which may link to zonal shifts in the jet stream. This is key. Significantly reducing the CO2 sink in the MAB, leaving more CO2 in the atmosphere. Wind speeds were also generally slower in the South Atlantic Bight from average during all marine heat wave months. This indicates wind speeds tend to decrease CO2 uptake during the carbon dioxide sink months, but counteract the impacts on marine heat waves on flux during the carbon dioxide source months. However, large standard deviations in wind speeds in both regions suggest that the effects of wind speed vary depending on the individual event. Okay, so let's take a look at figure 4. Wind speed's anomaly, right? So again, the upper row is for the mid-Atlantic Bight, the bottom row is for South Atlantic Bight, and like we saw earlier, they break it down in all the marine heat wave months, those above the 75th percentile and those below the 75th percentile. Here. So what do we see here? All right, they break it down to sink months, source months, and all combined. The wind slows down more so during the months when carbon dioxide is a sink into the ocean. It slows down, but not as much for when carbon dioxide is a source. In other words, the CO2 in the ocean goes back to the atmosphere. And when you combine it all, your overall speed still is slowing down. So what this is telling is that, as we just saw in the description, okay, little reminder of what was said in the description, reduced wind speeds basically reduces the CO2 sink in the MAB. So when they're slower, the sink reduces. In other words, the ocean's uptake of CO2 reduces, as they're showing here. And then here we have an increase in wind speed, which may counteract, as indicated by the shorter error bar here, the uptake. And this is combined. And below the 75th percentile, pretty much the same. And we really, just look at this. Really not much going on here with the SAB. Really not too different here. So, the underlying dynamics between the marine heat waves and the CO2 flux. During the 2012 I keep thinking M is marine. During the 2012 Mid-Atlantic Bight event, the extremely warm SSTs resulted in a significant increase in the partial pressure, ultimately reducing the Mid-Atlantic Bight's ability to take up CO2. In contrast, despite the extremely high temperatures during the 2017 South Atlantic Bight event, non-thermal drivers dominated the increase in the partial pressure. In April 2017, the increase in the partial pressure of CO2 was accompanied by a sea surface salinity change of a reduction of 0.95 practical salinity units in that region, corresponding to a change in, TA for total alkalinity of minus 0.1 micromoles per kilogram, using the linear relationship. TA is equal to that equation. Given a climatological dissolved inorganic carbon value, that's what DIC means, of 2015 micromoles per kilogram, this reduction in total alkalinity would lead to a plus 73.8 microatmosphere increase in partial CO2 levels. In the Mid-Atlantic Bight, CO2 flux into the ocean significantly decreased during marine heat wave months, especially under weak wind conditions in winter. This is particularly true for the atmospheric type of marine heat waves that were driven by anomalous air-sea heat flux. In the case of atmospheric-type marine heat waves, perturbations in the atmosphere can lead to decreased wind speeds and downward heat flux, both resulting in abnormally warm sea surface temperature. These phenomena have been attributed to the zonal shift of the jet stream. This is probably the most important pile of sentences in this study. In the case of atmospheric-type marine heat waves, perturbations in the atmosphere can lead to decreased wind speed and downward heat flux, both resulting in abnormally warm sea surface temperature, and this is attributed to the zonal shift of the jet stream. Considering that winter marine heat wave events above the 75th percentile also coincide with reduced wind speed, it is plausible that this mechanism contributes to the occurrence of these marine heat wave months. We therefore expanded upon the mechanism proposed by Chen et al. In 2014 to explain how marine heat wave events impact CO2 flux in the mid-Atlantic Bight during winter months. That's figure 5. In the mid-Atlantic Bight, the northward shift of the jet stream during winter causes a reduction in wind speed, leading to a decrease in latent and sensible heat fluxes. This hinders heat loss from the ocean, results in warmer sea surface that induces the marine heat wave event. These elevated temperatures increase the partial pressure, and the occurrence of weakened wind speeds further reduce CO2 uptake by the ocean. So here's figure 5. Okay, let's look at the caption. Conceptual diagram of mechanisms connecting marine heat waves and CO2 flux in the mid-Atlantic Bight. Solid arrows indicate increasing vectors or fluxes, and the dashed arrows represent decreasing vectors. The numbers represent the order of occurrence for the respective processes. Okay. So this is the upper atmosphere. The black line here is the normal position of the jet stream. When the jet stream shifts northward, look what happens. Right? So it shifts northward, and therefore that reduces wind speeds and the downward heat flux anomalies. So you start with the jet stream shifting northward. The wind speeds reduce. A downward heat flux anomaly happens so that sea surface temperatures increases, the partial pressure of CO2 in the sea increases, and the result, less CO2 uptake. There's your dashed arrows. Dashed arrows. So decreasing uptake, decreasing wind speed, increasing downward heat flux. In other words, yeah, ocean's absorbing the heat. This, I think, ties it all together. I know it got really technical here, but like anything else, they're trying to look at more than one parameter that explains the observed results. If they were to have done, say, a regression analysis, what is the contribution of each of the parameters? We had a hint earlier when they said that the marine heat wave, explains 68% of the observed information. So what's the other 32%? Probably wind activity. And that's what they're basically doing. Summary and conclusions. All right. So the sensitivity of the carbonate system to sea surface temperature variability indicates extreme temperatures during marine heat wave events can influence carbon transfer between the atmosphere and the ocean. Interestingly, we found that while the two most prolonged marine heat wave events in both regions resulted in basically large positive flux anomalies, in other words, CO2 going from the ocean to the atmosphere, marine heat waves alone were insufficient to guarantee positive flux anomalies. So what they did was they identified specific conditions that led to what could explain the changes in the flux. In the South Atlantic Bight, it wasn't just marine heat waves alone, but variations to other factors than temperature, such as wind. Okay? Whereas in the Mid-Atlantic Bight, the marine heat waves did play a more significant role, though there is contributions from non-thermal drivers, wind, that can impact. Whereas in the Mid-Atlantic Bight, yes, marine heat waves plays a more significant role, though non-thermal drivers, wind, were also important to produce positive changes in the partial pressure of CO2, impacting the overall flux rate. We add that the northward shift of the wintertime jet stream in the Mid-Atlantic Bight results in weakened wind speeds and downward heat flux, leading to increased CO2 and increased CO2 partial pressure, increased SST, leading to a increase in the positive flux from the ocean to the atmosphere, or conversely, leading to a decrease in the ability of the ocean to uptake CO2. So, see if I can sum this all up now. You have marine heat waves, you have high SST. We can measure the impacts on it, chemically speaking, that we see an increase in the partial pressure of CO2 in the oceans. As you increase the partial pressure, the ability to draw down further CO2 from the atmosphere decreases. Also, don't forget, warmer waters means gas solubility decreases, further limiting the ocean's ability to pull down more CO2 from the atmosphere. So what they're basically saying was, overall, they did the differences between the two regions. Marine heat waves results in either a delta P being positive, in other words, indicating a flux of CO2 from the ocean to the atmosphere. Now, that flux can also be the result of warmer temperatures, gas solubility decreasing, so that CO2 is now outgassing, as well as inability to draw down more CO2. Marine heat waves alone, sea surface temperatures alone, an increase in that alone is not enough to explain the changes in the partial pressure or the changes in delta P. You have other factors. Wind. If the wind's picking up, well, first of all, higher winds, you can have a cooling effect on the surface water. And you have increased mixing, so that enables the ocean to pull down CO2. Weakened winds, that goes away. You don't have the evaporative cooling, you don't have the increased mixing, so that will result in the CO2 staying in the atmosphere, not going into the oceans. And then when you couple that with the higher sea surface temperature, you're going to really not pull down CO2 from the atmosphere into the ocean, and may even have an outgassing as measured by a positive delta P, outgassing of the CO2 back to the atmosphere. And we're seeing this. This is one study that's showing this. Like everything else, all these parameters work together to create the results, the phenomena that we see. Now, they're talking about the Mid-Atlantic by in 2012, even the SAB in 2017. That's 7 years ago. We saw what happened last year in 2023 with the off-the-charts sea surface temperature across the entire Atlantic basin. Oh, I wonder if they're going to do a follow-up on last year and publish those results. I would love to see that, because I bet you're going to see a delta P with really high positive values. And you're going to see massive outgassing of CO2 to the atmosphere, and accompanied by a massive non-drawdown of CO2 from the atmosphere. So yes, this is got a little kind of crazy and a little technical here. Hope I didn't confuse everyone. But basically, warmer waters increases partial pressure of CO2, limiting its ability to draw down CO2 from the atmosphere, and enhances its ability to outgas CO2 to the atmosphere. It can be aided or mitigated by wind, depending on the wind speed, basically. And we're also seeing what? We'll go back down to figure 5 here. Jet stream shifting northward. We're seeing a jet stream going all over the place. And that impacts the winds. It would not surprise me. They concentrated off the east coast of the U.S. There was a reference to studies in the North Pacific Gyre. I would like to see similar studies done elsewhere, across all the oceans, to see exactly what's going on, to quantify better the flux of CO2 that's taking place, and to see, take all these areas. What is the overall for the entire planet? What is the overall net delta P for the air-sea flux, air-sea exchange? If it's positive, that means CO2 for all the oceans, for the planet, is going back from the oceans to the atmosphere. And that the oceans, which have been for many years, many centuries, been a sink for CO2, well, we're seeing the increasing sea surface temperature. It now may become a source of CO2. And if that's the case, oh boy, we're in for it. And one other thing, some of the other non-thermal factors was, of course, the mixed layer and the productivity. I mentioned that earlier. We have to consider all of those. But in this study here, they really seem to have concentrated on wind and thermal aspects, which is fine. But remember, with increasing temperatures, decreasing vertical sinking, we are seeing increasing stratification and declining productivity. So that factor may soon be non-significant. But as I said, I would love to see a delta P for the entire oceans. And if it's positive, as I just said, but I'm reiterating it, we're in big, deep doo-doo. I will, as I state, I will leave the URL both in the comments and in the description. And of course, they'll have the chapters here for those who are interested in looking at this paper, pulling up the supplementary diagrams as well. So, thank you for your time. I hope you found this interesting and informative. And we'll talk next time. If you stuck around to the end of the video, thank you for watching. Be sure to give this a thumbs up, as it really helps the channel. And if you can, please support me either on Patreon and or buy me a coffee. Details in the description box below. Thank you.